We have, over the last several days, been talking about the analysis of collisions and explosions. In each of those collisions and explosions, we found that momentum is conserved. We're now going to break down collisions into two separate categories. In both of those categories, momentum will still be conserved. Things aren't changing as far as momentum goes. Momentum will always be conserved as long as we have an isolated system. But we are going to distinguish between two types of collisions in another way. That other way is with kinetic energy. The first type of collision is what we're going to call an elastic collision. An elastic collision is a collision in which kinetic energy is conserved. So is momentum. But that's a given because momentum is always conserved. What do we mean by conserved? Kept, stays the same. So momentum, of course, stays the same. That's the law of conservation of momentum, and it'll always hold whether it's elastic or not elastic. But kinetic energy will be conserved only in an elastic collision. Versus the other type of collision that we have, which we call an inelastic collision. Momentum is still conserved in an inelastic collision, but kinetic energy is not conserved. What do we mean by that? Kinetic energy is not conserved. What happens to it? It changes. If it's not conserved, well, it's certainly not going to be created, so it's going to be lost. If kinetic energy doesn't stay the same, it's going to be lower for the final kinetic energy after the interaction has taken place than before the interaction has taken place. In other words, EKI will be greater than EKF if we've got an inelastic collision. Momentum will stay the same, kinetic energy will be lost. For an elastic collision, both momentum and kinetic energy stay the same. Got a little chart to summarize it here. Is momentum conserved in an elastic collision? The answer is yes. What about an inelastic collision? Yes. Momentum is always conserved as long as we have an isolated system. What about kinetic energy? Elastic, is it conserved? Yes. That's how we define an elastic collision, a collision in which kinetic energy stays the same. What about an inelastic collision? We'd say no for this one, right? Kinetic energy is lost in an inelastic collision. Now, this last column is one that we haven't talked about yet over the last few minutes. Do the objects bounce apart? In an elastic collision, the objects must bounce apart, always. In an inelastic collision, the objects sometimes bounce apart. If you have a collision in which both objects stick together, you know it's inelastic. It's got to be inelastic. Kinetic energy must be lost. Because if it's elastic, the objects always bounce apart. If you get a collision in which the objects bounce apart, we don't know what it is. Could it be elastic? Yes. Because collisions that are elastic always have the objects bounce apart. But sometimes the collisions that are inelastic also have the objects bounce apart. So if they stick together, it's got to be inelastic. If they bounce apart, it could be either elastic or inelastic. Kinetic energy could stay the same or it could be lost. We're not sure simply by looking at it. Well, if we're not sure simply by looking at it, how do we determine whether it's elastic or inelastic? Let's calculate the kinetic energy. And let's compare the initial kinetic energy to the final kinetic energy. The initial kinetic energy can be found by multiplying 1/2 mv squared for each object that we have before the collision. 1/2 m1 v1i squared plus 1/2 m2 v2i squared plus 1/2 m3. However many objects we have a term. 1/2 mv squared for each object that we have before the collision takes place. Let's get a value for kinetic energy there. Then let's calculate the final kinetic energy. Let's say EKF is equal to 1/2 m1 v1f squared plus 1/2 m2 v2f squared. Could that change? Sure. If the objects stick together, then we would only have one term, 1/2 mvf squared. If there were three objects, it would be 1/2 m1 vf squared plus 1/2 m2 v2f squared plus 1/2 m3 v3f squared. But you see what we're doing here. We multiply 1/2 mv squared for each object that we have both before and after the collision. And then we add up the initial kinetic energy, we add up the final kinetic energy, and then we compare them. If we find that these two numbers are the same, then we know it's an elastic collision. If we find that the final kinetic energy is less than the initial kinetic energy, what does that mean? It's inelastic. Right. If we find that the final kinetic energy is more than the initial kinetic energy, what does that tell us? It tells us to do it again because we made a mistake. If the final kinetic energy is more than the initial, we're wrong. The final kinetic energy will always be the same or less than the initial kinetic energy. If we're talking about an elastic or inelastic collision, okay, if that's how we're trying to distinguish it, then it's always going to be either the same or less, never more. Now, it is possible to get more kinetic energy afterwards than we have before, but we don't categorize. That would be in the case of an explosion, right? You fire a gun, what's the initial kinetic energy? 0. What's the final kinetic energy? Something. The final kinetic energy is more than the initial kinetic energy. But we don't categorize that as elastic or inelastic. So if in the context of an elastic-inelastic collision, you're trying to categorize it, the final kinetic energy will either be the same or it will be less than the initial kinetic energy. Okay, we're going to do a problem in just a moment here, but I want to point out a couple of common mistakes before we do that problem. First common mistake, do not set these equal to each other. Okay, a lot of people will do this. They'll automatically just set EKI equal to EKF, and then they'll say 1/2 m1 v1I squared plus so on and so on and so on equals whatever the final kinetic energy is. What's wrong with that? Why can't we set those two equal to each other? They don't always equal each other. If it's an elastic collision, all right, then you can set them equal to each other. But usually the question asks you, is it elastic? The only time you can ever set them equal to each other is if the question tells you it's an elastic collision. Does that make sense? Because if it doesn't tell you, you don't know whether it's elastic or not. So don't set them equal to each other. The second common mistake, if the mass is the same, what a lot of people will try to do is cancel out the mass. Why can't we cancel out the mass, even if the masses are both the same? Let's say it's 10 kilograms right here, 10 kilograms right here. Why can't we cancel out the 10 kilograms? In order to cancel something out, it has to appear in every term. It does not appear on the left-hand side. So don't cancel it just because it appears in both terms on the right-hand side. It's got to appear on the left-hand side as well, and it doesn't. So don't cancel out masses even if they're the same. Finally, the third common mistake is forgetting to square the v. What a lot of people will do is kind of get mixed up between momentum and kinetic energy. They'll say 1/2 mv as opposed to 1/2 mv squared. I'll tell you this right now. If you use 1/2 mv versus 1/2 mv squared, you will find every single time that it's elastic, even when it's not. So there's no point in even doing it. If you're going to forget to square the speed, you're always going to find the initial is equal to the final. But it's not always equal to the final. So let's make sure we're using 1/2 mv squared as opposed to 1/2 mv. All right, let's take a look at our problem. Let's keep those common mistakes in mind as we go to do this problem, and we'll see how easy this stuff really is. This one says a 0.16 kilogram billiard ball is traveling at 0.5 meters per second to the north. It strikes a stationary snooker ball and rebounds at 0.023 to the south. The snooker ball moves off at 0.465. Is the collision elastic or inelastic? We'll call this M1. We'll call this M2. We'll call this V1I. We'll call this one V2I, the stationary 0.180 kilogram ball. We'll call this one V1F. It says the 0.16 kilogram billiard ball rebounds at 0.0230 meters per second. We'll call this one the snooker ball after the collision takes place, V2F. What have I not done in this question that I've done in every single question we've done so far this year? Yep. I haven't circled the north and south. I haven't done that to distinguish between directions here. There's nothing wrong with doing that. I can do that in every question, including this one. But why have I not done it in this one? Why have I not bothered to distinguish between north and south in this question? Because kinetic energy is a scalar, so the direction doesn't matter. If you circle it, that's great. You recognize that one's north and one's south. But if you don't circle it, it doesn't matter because we treat them both in the exact same way anyways. In this question, because we're dealing with kinetic energy. All right, let's do this here. EKI is equal to EKF. So we say 1/2 m1 v1 I squared plus 1/2 m2 v2 I squared, right? Equals 1/2 m, just right? What's wrong? I equaled them? Yeah. And what's wrong with that, Rob? No, why not? Can't do that. You're right. I can't do that. Why not, though? It's asking if it's elastic. If I do this, I'm saying it's elastic. I'm not solving anything. I'm saying it's elastic. And we don't know that it's elastic. So let's calculate EKI and EKF separate from one another. Again, the only time you can ever get away with that is if it tells you this collision is elastic. All right, EKI is equal to 1/2 m1 v1I squared plus 1/2 m2 v2I squared. We don't have to worry about canceling out the masses here because they're different masses. But even if they're the same, remember, you can't cancel them out. Mass 1 is 0.160 kilograms, and v1I is 0.500 meters per second. Let's square that. v2I is equal to 0, so let's just cross off that entire term. 0.5 squared is 0.25 times 0.08 is 0.02, I think. 0.0200 joules. That's the initial kinetic energy. We still don't know whether it's elastic or inelastic. We've got to get the final kinetic energy to figure that out. Let's calculate EKF. Let's say 1/2 m1 v1f squared plus 1/2 m2 v2f squared. Hey, what would we have done? How would this change if both of these objects stuck together? Wouldn't change dramatically, but it would change a bit. How would this look different if they stuck together? Yeah, there'd be one term in the end, right? It would be 1/2 m vf squared. All right, let's go 1/2 of 0.160 times v1f squared, which is 0.0230 squared. Notice how I have not put a negative in there? Michael, why didn't I put the negative in there again? Right, speed's a scalar, kinetic energy is a scalar. We don't worry about direction. Let's add to that 1/2 of m2, which is 0.180 times v2f, 0.465 squared. What do we get when we do the math on that one? Final kinetic energy, 0.0195, I think it was, if I remember. 0.0195 joules. Is it elastic or inelastic? We would say this is inelastic because there's kinetic energy lost. Now, there's not very much kinetic energy lost. If I rounded that to one digit, in fact, I would get 0.02, and I would get 0.02. That would tell me it's elastic. So how do we know where to round to here? How do we know whether to go to one digit there, or two digits, or three digits, or whatever? That affects what our answer is, whether it's elastic or inelastic. Round it to the right number of digits. Let's look back at our data. 3 digits, 3 digits, 3 digits, 3 digits, 3 digits. Final answer should be 3 digits. If we round it to 3 digits and it's equal to the other number, then it's elastic. If it's not equal, then it's inelastic. Doesn't matter if to one digit it's elastic or not, because we're supposed to round this to 3 digits. This is one of the few places where you've got to be really careful with significant figures. In most of the questions that we see, in the end, the question tells you, round it to 3 digits if it's a test question. This one doesn't. This one might say, is it elastic or inelastic? And you've got to determine how many digits to round it to determine whether it's elastic or inelastic. Most times it's not going to be this close, I'll be honest with you. Most times it's going to be further off than that. But every once in a while it is going to be this close. Quick question. Most times we have a collision, it's inelastic. The vast majority of the time it's inelastic, including this one. But this one was really, really close to being elastic. This is about as close as we'll ever get in the real world to having an elastic collision. Anybody want to take a stab at why this would be really close to elastic, but most collisions are inelastic? No, not friction, because we want to keep outside forces from coming into play there, right? It's not a friction thing. It's an energy conversion thing. You guys learned in Science 10 something called the second law of thermodynamics. First law of thermodynamics said energy can't be created or destroyed, only transformed. Same as the law of conservation of energy. The second law of thermodynamics said you can't even break even. In other words, whenever you have an energy conversion, you always lose a little bit of energy. Do you remember that? You guys remember that from Science 10? What happens when you drop a basketball on the floor? What happens to the basketball as it hits the floor? It squishes, it compresses, right? As it compresses, you have kinetic energy transformed into elastic potential energy. And then as it goes back up into the air, you have elastic potential energy converted back to kinetic energy. Every time you convert kinetic to potential and potential to kinetic, you lose a little bit of energy. So when that ball goes back up into the air, there must be less kinetic energy than we started with when it was falling. Why don't you have a lot of kinetic energy lost in this one? How much do these billiard balls squish when they hit each other? Very little. And if they don't squish very much, then there's very little energy conversion taking place. And if there's very little energy conversion taking place, then we're going to have very little kinetic energy lost. When's the only time you can have a truly elastic collision? This is close. When's the only time you can have a truly, perfectly elastic collision? No. Not an isolated system. We're assuming an isolated system here for all of these. No. Good guess. Space, good guess. What is the only thing that can't compress at all? Pool balls barely compress. Marbles barely compress. What's the only thing that can't compress? Something that's as small as it can possibly get. Subatomic particle. If subatomic particles collide, certain types of subatomic particles collide, fundamental particles, then they can't compress. If they bounce off each other, there can't be any conversion to potential energy there, right? And if there's no conversion to potential energy, then it's got to be elastic. So the only time you can ever have a truly elastic collision is when it's subatomic particles bouncing off each other. That make sense? Yep. No, when they hit each other, they just bounce off of each other. And the kinetic energy before ends up being equal to the kinetic energy after. The speed can change because it can be transferred from one to the other. But in the end, the total kinetic energy isn't going to change. It's going to stay the same. Okay? All right, let's take a look at these two practice problems and see what you can do with those over the next few minutes. All right, guys, if we're having no trouble with this, I will assign your homework. Your homework is going to be page 486, number 1 to 11. Here's the good news. It's not due till Friday. Page 486, number 1 to 11, due on Friday. The reason I'm not making it due until Friday is because you may have an opportunity in class tomorrow to work on it, and we won't have an opportunity to go over it in class tomorrow, even if it was finished for tomorrow. So if you want to get it done for tomorrow, that's fine, but you may have an opportunity to work on it in class, and we won't be going over it until Friday.